Have you ever wondered where the power to light up entire cities comes from? It's a question that might have crossed your mind as you switch on a lamp or plug in your phone. The answer is much smaller than you might think, and it lies in the heart of an atom. Atoms, the building blocks of everything, hold an immense amount of energy in their tiny frames. They're like miniature power plants, ready to release their energy when the right conditions are met. Now imagine harnessing that energy on a large scale. That's precisely what nuclear power plants do. These massive structures tap into the atomic energy, converting it into electricity that powers our homes, schools, hospitals, and cities. This process of energy conversion is happening right now, all around us, lighting up our world, powering our lives. It's an incredible testament to human ingenuity and the power of science. Indeed, the secret lies in the heart of an atom. So what's in an atom that holds such immense power? Let's delve into the heart of the matter and take a closer look. Imagine an atom as a tiny solar system. At the center of this universe, we find the nucleus. This compact core is where the magic happens, and it's made up of positively charged protons and neutrally charged neutrons. The rest of the atom is mostly empty space, where negatively charged electrons orbit the nucleus in a dance that's as intricate as it is infinite. It's within the nucleus that we find the source of an atom's immense power. This power comes from a process known as nuclear fission. Now, what is nuclear fission, you may ask? Well, it's a kind of alchemy that only nature can perform. It's a process where a heavy atom like uranium or plutonium splits into two or more lighter atoms. The splitting of the atom doesn't just happen on its own. It needs a little push, a little energy. This comes in the form of a neutron. When a neutron strikes the nucleus of a heavy atom, it causes that nucleus to become unstable and split. This split releases a massive amount of energy, but that's not all. The splitting atom also releases more neutrons, which can then strike other atoms, causing them to split and release even more energy. This creates a chain reaction, a domino effect of energy release. Each split triggers another, each reaction fuels the next. And here's the astounding part. The energy released in this process is mind-boggling. The fission of a single atom releases about 1,000,000 times more energy than a chemical reaction, like burning a molecule of gas. This is the immense power that's harnessed in a nuclear power plant. So when you flick on a light switch and your room illuminates, remember this: that light is powered by the splitting of atoms, by the incredible process of nuclear fission. And that, folks, is the incredible process of nuclear fission, releasing energy on a colossal scale. Now, how does a nuclear power plant harness this energy from atoms? Let's dive in and find out. A nuclear power plant is a complex system, but its core function is to generate heat, which then produces steam, which in turn drives turbines to generate electricity. At the heart of a nuclear power plant is the reactor. This is where the magic happens, where atoms are split apart in a process known as nuclear fission. The reactor is filled with fuel rods, which are long, slender tubes packed with pellets of uranium-235 or plutonium-239. These are the heavy isotopes that are prone to fission. Now, if we left these fuel rods to their own devices, they would heat up uncontrollably. That's where control rods come in. These rods are made of materials that absorb neutrons, the particles that drive the fission process. By adjusting the position of the control rods, we can control the rate of fission, and therefore the heat produced in the reactor. The heat from the reactor is then used to heat water, but not just any water. This water is under high pressure, which prevents it from boiling, even at temperatures above 200 degrees Celsius. This high-pressure, high-temperature water is then passed through a heat exchanger, where it heats a separate supply of water, turning it into steam. The steam then drives a turbine, which is connected to a generator. As the turbine spins, it turns the generator, producing electricity. Once the steam has passed through the turbine, it's cooled back down into water in a condenser, and the cycle starts all over again. It's a beautifully efficient system, where the only waste product is heat, and even that heat can be used, in some cases, for district heating systems, providing warmth to homes and businesses. So that's how a nuclear plant converts atomic energy into electricity, lighting up our cities and homes. It might sound complex, but it's really just a matter of controlling a process that's been happening in the universe for billions of years. And that's pretty amazing when you think about it. But wait, isn't nuclear energy dangerous? Well, it certainly can be, but it's also one of the most tightly controlled and regulated industries on the planet. Every nuclear plant is a fortress of safety measures designed to keep both workers and the surrounding community safe. The first line of defense in a nuclear plant is the containment structures. These are robust, fortified buildings designed to withstand even the most severe conditions. They are made of steel-reinforced concrete several feet thick, and they are designed to contain radiation, even in the event of an accident. Inside these structures, you'll find the nuclear reactor, where the magic of nuclear fission happens. This is where the atoms split and release energy. But these reactions generate a lot of heat, which if not controlled could lead to an accident. That's where the coolant systems come into play. These systems circulate a coolant, often water, around the reactor to absorb the heat and keep the temperature stable. The coolant systems are meticulously monitored and controlled. If the temperature gets too high, the system automatically shuts down the reactor to prevent overheating. This is just one of many automatic safety systems in place to prevent accidents. But it's not just about the physical structures and systems. The people who work in nuclear plants are also a crucial part of the safety measures. They are highly trained professionals who follow rigorous safety protocols. They perform regular checks and maintenance, and they are trained to respond quickly and effectively in an emergency situation. Furthermore, these plants are subject to regular inspections by regulatory bodies to ensure that all safety measures are being followed. These inspections are thorough and unannounced, ensuring that plants are always operating at the highest safety standards. So, while it's true that nuclear energy can be potent, and yes, even dangerous, it's also one of the safest forms of energy production we have. The safety measures in place are extensive and robust, and they are constantly being reviewed and improved upon. Yes, while nuclear energy can be potent, we have strong safety measures in place to protect us. With all this potential, what does the future hold for nuclear energy? As we delve into the future prospects of this powerful energy source, two key developments stand out: the evolution of nuclear fusion and the advent of small modular reactors. Nuclear fusion, the process that powers our sun, is the holy grail of the nuclear energy world. Instead of splitting atoms, as we do in nuclear fission, nuclear fusion combines light atomic nuclei to form heavier ones, releasing a massive amount of energy. It's a clean, virtually limitless energy source with the potential to revolutionize our energy landscape. Today, the challenge lies in creating and maintaining the extremely high temperatures and pressures needed for nuclear fusion to occur. But with ongoing advancements, the dream of harnessing the power of the stars may soon become a reality. On the other hand, small modular reactors, or SMRs, represent a shift in nuclear power plant design. Traditionally, nuclear plants have been large, complex structures that require significant investments of time and resources. SMRs, however, are smaller, simpler, and cheaper to build. They can be manufactured off-site and transported to their destination, reducing construction times and costs. These reactors are designed to be safer, more flexible, and more efficient than their larger counterparts, making nuclear energy accessible to more regions around the world. But perhaps the most compelling argument for the future of nuclear energy is its role in combating climate change. As we grapple with the urgent need to reduce greenhouse gas emissions, nuclear energy offers a reliable, large-scale source of low-carbon power. It can complement renewable sources like wind and solar, providing consistent energy output even when the wind isn't blowing or the sun isn't shining. As we strive for a cleaner, brighter future, nuclear energy stands as a beacon of immense potential. It promises not only to power our homes and cities, but also to help us tackle one of the greatest challenges of our time: climate change.